Thank you very much, Andrea. So the last talk will be on how to use retrospective data from Biobanks and repositories, Professor Luis Martí-Bonmatí from Valencia, Spain.
Okay, thanks a lot for the presentation, and I will try to share with you in these 20 minutes, which were also our troubles in this setting on putting proteomics and imaging biomarkers into clinical practice. And we try a slightly different approach on the last years, trying to use large retrospective data from biobanks and imaging repositories. So regarding conflict of interest, well, I have no important one. I was co-founder of one company that is related to radiomics and imaging biomarkers, but I have no shares. But the main conflict of interest is that on the last 20 years, I really thought that imaging biomarkers and radiomics were going to change the way radiology is doing. And now I do understand that we thought we knew how to do it, and we were so proud on what we were doing. And on these last 2 years, things have changed, because there is a huge amount of variability on what we are doing. And I will try to share with you how to try to decrease that variability, taking into consideration what we now know as real-world data, which is what are we doing daily in our clinical practice. So first, let's go into why do we need computational medical imaging and endpoints, those clinical questions we have to answer. And the reason for that is because people, individuals, they are different, and the diseases, they are also different, and there is a huge heterogeneity between diseases, lesions, organs, and people. And also we have a huge amount of questions to answer with the tools we want to apply by using radiomics, biomarkers, biobanks, data analytics, coming from predisposition to early detection, characterization, phenotyping, natural history, response to treatment, and so on. So to do that properly, if we really want to have an impact in clinical practice, maybe we have to rethink what we are doing. And this is the steps most of us are following in our daily practice. We need an idea. I want to measure whatever biological thing we need is important for us. Then we need to acquire images, prepare them, start image processing, signal analysis, dynamic modeling. At the end, measure those metrics we already saw this morning. Try to do that on a small sample of patients that will be extremely well defined, which is called internal validation with the reference values, take care of the biases, enlarge the amount of patients you are studying, try to have an external validation, and at the end, translate that into clinical practice through the structure report. And we are really willing to have a structure report with automatic tumor volume segmentation, evaluating the so many different habitats or heterogeneous clones you might have there. But in clinical practice, we are not doing this. And we are not doing this because it's extremely difficult, mainly because of variability. Variability is huge, and we have to take care on the technical validation, which means the redundancy of data we already saw this morning, the precision and stability of our results. That means repeatability or variability without changes. If we do test, retest, will those metrics change? reproducibility, which is variability when we have changes. What happens if we have different machines, different upgrades, different number of detectors, different repetition times or whatever. Maybe those things are not really huge, but they will introduce a change on the reproducibility of our results. Also, it's extremely important to look for the accuracy of our measurements, which means, do we really know the ground truth we are willing to measure? And most of the time, we have to go to phantom studies. And which is the gold standard we are using? Is the gold standard pathology? And is pathology really a stable and reproducible gold standard? So with all these technical validation studies, if we succeed on them, then maybe we have to go to the relevance of our measurements. I mean, that means the impact of the measurements we are doing, which means the correlation with the clinical endpoints to be a biomarker, a surrogate marker of whatever we want to measure in clinical practice, like response to therapy or aggressiveness or probability to have metastasis or whatever, and of course at the end the impact on healthcare pathways. So variability is huge and our impact is quite low. And let me share with you what we are doing in clinical practice. This is a hepatocellular carcinoma in cirrhotic patients. This is what we do in our hospital. And guess, we are only measuring the number of lesions, the size of the lesions, and nothing more. I mean, that's our approach. Once we know that's an HCC, radiomics and imaging biomarkers is number and size. And we are something like 10 years doing intravoxel incoherent motion, pharmacokinetic modeling on the trying to look for the aggressiveness of the tumors, and we didn't succeed on that. I mean, we are not having any impact on clinical practice, although there is a huge amount of work trying to have an impact on the clinical practice. And from my understanding, the reason for that is because of variability of our results in the real world practice. And that's because we are working with extremely high heterogeneous medical images. I mean, so many different vendors, releases, upgrades, protocols, and those things limit our biomarkers approaches in these replication studies. And this is something that, although we try to do it quite nice and quite beautiful, it's really a limitation. So do we really have the right answers in oncologic imaging to provide data to have an impact on clinical practice? It's our approach on radiomics and data modeling or signal modeling, biomarkers, imaging biomarkers development, a good one. Why imaging answers to biological questions like those ones we saw from phenotyping, grading, aggressiveness, staging, whatever, are not really, do not have a real clinical impact in daily practice. And from my understanding, the reason is because, again, variability, truth, uncertainty. And that means that for whatever we try to measure, if that is going to be representative of a reality, it must have a relationship with is an ambiguous with the physical or chemical or biological process we are measuring, okay? And we do have to recognize that signal comes from box cells, and those box cells, they have so many different components and properties within them, and they are also reconstructed on so many different ways that it's really hard to get objective measurements from them. Now let's go into certainty and evidence. If we go into what is recognized as the best way to perform clinical research today, we have to realize that to have a causal inference of relationships between whatever we measure and the clinical reality, most people, most centers, most journals recognize prospective experimental studies, mainly clinical trials, either non-control or control with control versus interventions, without or with randomization of the sample as the best evidence. And on the level and grading of evidence, those based on randomized control trials, mainly with meta-analysis, or even heterogeneous prospective comparative studies, those are the best ones. But most of us, we like to work with retrospective data because we have a huge amount of data in our PACS system. We can have repositories of images coming from so many different other hospitals, and it will be much easier to increase the knowledge we do have if we are able to perform high quality clinical research on retrospective clinical data with the data we have that comes from the real world, from those extremely heterogeneous cases we do have in clinical practice. So maybe there is a way to perform high quality retrospective observational studies on a longitudinal base with cohort or case control studies. And the reason for that is because the, let's say, gold standard of clinical research maybe is not universal, the results. Maybe they are not reproducible. Maybe they cannot be validated, or maybe they might not be relevant on what we are doing. And just to have a view on that, there is a concern on the scientific community on the crisis of reproducibility. And that means, and this is a nice paper on Nature some years ago, that most of the authors that publish in Nature recognize that there is a lack of reproducibility of the results that are being published today on the highest quality journals we do have. And we might think, well, you know, that's not medicine, that might be psychology, no? I mean, this is chemistry, biology, physics, engineering, medicine, earth, and others. Most of us are within 50 and 60% non-reproducible resource, which is a huge amount if we are going to take decisions based on those prospective trials, okay? So let's go maybe deeper into variability, certainty, and evidence. The first thing to come into mind is that maybe thinking that evidence-based medicine will give us all the relevant information to take decisions is not a truth. And we recognize that. And on the scientific community, there is a growing interest to use real-world data, the data we use in our daily practice, to address those clinical and policy-relevant questions that might not be properly answered with clinical trials. Because sometimes clinical trials are not constructed to answer the right clinical questions. And this is now the debate between should we use real-world data or maybe this research-controlled data, which the pros and cons they do have. Let's see them. For prospective studies and research-controlled data, the cons are that they are using a limited size group. They are not huge. There is a huge precise inclusion criteria, so we are sampling a small portion of the universe. They are extremely expensive, and there is limited evidence because of this subsampling bias. But the good thing is the control and homogeneity of the sample. That's the extremely good thing. Let's go into the prospective studies with real-world data. The good things are maybe data heterogeneity will be more representative of the population we are evaluating every day in our practice. There is a need to control data quality, but we can do that through data scientists, as we saw this morning. And the pros is that the population will be much larger. We will include comorbidities, because that's the real life. There is a large temporal window. We will have so many more cases. The cost is much lower. And at the end, we will provide what is called real-world evidence. That means evidence that will work in our daily practice. So for these image-related scientific studies to obtain causal inference, and the challenges of image-related research methods, which are the ones we are doing with these radiomics and imaging biomarkers approaches, we have to define that maybe observational studies with retrospective data will be good for that. We have to have as population-based real-world data, large samples as possible. Whatever we obtain should be universal and general, reproducible and cost-effective. And of course, we will have to work on those levels of phenotyping, predicting response, and surrogate outcomes. And the trouble is that sometimes most of the trials performed on prospective data, they have small data samples, undersampled data, and reproducible data. So let's go into how to pick up data from real-world life. Those are the real-world data repository that comes to a central repository coming from, of course, clinical trials, registries from rare diseases. We can go there. We can have open access public biobanks, as we already saw this morning. We can ask our radiological information system or the community radiological information system or the country imaging biobanks to provide that data with sometimes also structural reports. And of course, we can ask the electronic health records from the hospital information system to give us as the probability to obtain objective data from the real world on a large scale, adequate, complete, organized, and let's say standardized on the way we pick up the data as feasible. And to do that, one nice approach is the definition of biobanks, and imaging biobanks. That's the paper coming from the ESR, and those repositories, they have a huge amount of data that are available for clinical research and innovation in personalized medicine. There is quality control for sample collections, extraction, and protocols for the protection of the data and the regulatory and legal aspects for that. And we can apply these imaging biobanks, or we can recognize them as virtual banks that will help us to identify early biomarkers and imaging surrogates. So these biobanks, in our approach, they are expected to evaluate in silico on the computers and validate the impact of the biomarkers we can obtain from those images in silico on the computers to be able for early diagnosis, disease phenotyping, and all those things. So this is the way we manage our biobank, management of image collections, consultation, related cases to external databases like pathology or clinical aspects or genetics, image quality check, and benchmarking, because at the end, we want to construct the real-world evidence. And how do we do that? We have to follow the Strobe approach for longitudinal studies. And these are retrospective in silico observational studies that will have to eliminate all those confounding effects to allow causal inference. And we do that exactly the same way as prospective studies. I mean, we have to control recruitment, sampling, data collection, reference standard, technical specifications, the units and cutoffs and categories, the number, training, and expertise of the observers, and the blindness of what we are doing. And if we do that properly and we construct the pipeline to evaluate the data before we start the retrospective study, we will be able to have this comparative effectiveness research conducted as a target trial or a pragmatic trial, which will be able to give us the right answers. But even if we do that, do we have now the right answers with that data coming from the real world? Can the process be further improved? Our approach is that yes, that maybe using artificial intelligence will give us a lower variability and a better reproducibility on the data we take from those biobanks. And the two ways we want to do that is through virtual dissection and virtual biopsy. And let's see what's that. Virtual dissection is the use of convolutional neural networks or forestries or whatever approach we have from deep learning to extract organs and lesions. And we can do that. This is what we do now on liver imaging to calculate fat, iron, inflammation, and fibrosis. We also want to perform virtual biopsy with artificial intelligence, which is by the use of deep learning or convolutional networks, and this is our approach with the aggressiveness of prostate tumors, we will be able to pick up those regions or those with a signature, meaning a multivariable approach that has learned from handcrafted radiomics and imaging biomarkers. So if we do that properly, we will construct these repositories to develop artificial intelligence in clinical practice. And just to summarize, we have a huge amount of heterogeneity in image quality based on vendors, protocols, and updates. We do have continuous technological advances, so forget about image standardization. It will be never feasible. There is a huge amount of hardware and software changes. We have to recognize that that standardization will never arrive in the real-world data to obtain real-world evidence, and maybe the use of deep learning or convolutional neural networks will allow us to learn from that lack of homogeneity to have, let's say, normalized images that will be used to obtain data with lower variability and better reproducibility. That's our approach today. And this retrospective real-world data with, of course, a quality assurance checklist based on the Strobe for observational studies will give us the probability to use a huge amount of data, big data, that is behind us to obtain real-world evidence. And this is the last project we are involved now, where we use data coming from biobanks on 3 main countries in Europe, trying to develop a centralized data repository where we will train by artificial intelligence radiomics and imaging biomarkers using different models to answer phenotyping, treatment allocation, and patient prognosis in patients with neuroblastoma and diffuse pontine glioma. And we are using deep learning and convolutional neural network on most of those processes. And these are the projects we are working with that, or with artificial intelligence and oncology. This is the one we are now fighting for, and I hope we will be able to present some data on that. And this is another one with artificial intelligence in a completely different environment. So I hope the future is not on the standardization and clinical trials only, because that's a single center approach, is in the right use of retrospective and real-world data to obtain real-world evidence. Thank you.
Where is the future? Gathering data or synthesizing data, example via the GANs for medical imaging use? Luis, you kind of almost touched a little bit, or?
Well, I think the future is everywhere, no?
That's a very opportunistic answer.
No, I mean, all the approaches are good approaches, and we have, the trouble is that we do have different answers. And from my point of view, we need to approach really what we are doing in clinical practice to obtain data for clinical practice, trying to be as fast as possible on the innovation process. That's I think that will be the fast way to have a real clinical impact.
Any of the other speakers? Andrea?
I don't have any experience with synthesized data. I just have clinical data, so I don't think I'm the best person to answer that question, sorry.
I believe we don't really need synthesized data. We have so much digital data, we just have to find a way of accessing it. If you look at breast imaging...
That's true for breast, that's true for breast and for prostate, but not everything is the amount of data that breast has, actually. So I think synthesizing is valid, but in the right context, I think. So.
Yeah, I have to agree with what was said already. I think synthesized data make a lot of sense for numeric data. I'm not so sure about imaging. So for imaging, I'm not sure that we should use it if indeed what you said, we have a huge data set available.
Well, apart we don't lose the sight now, we're synthesizing CT from MRI and MRI from CT and from ultrasound. So actually we are going to be faced with looking at synthesized data, we like it or not. So I think we are, well, no, I think the reality is we prepare, no matter what we're expert on, we have to prepare for all the kinds of reality. I mean, some of the work we're doing is actually reconstructing the images from the raw data so they look completely the same without the need to worry about homogenization at the end. So I think the beauty of our community is that we all come from different angles, don't you think? And then we answer various questions. So I think there's one. It's one very interesting question. So excellent talk, complimentary to you, on breast. Raises the question if every AI black box needs to undergo rigorous clinical trial before becoming commercially available.
That's a tough question, and I don't think you're going to like the answer. I mean, if you really want to have someone take responsibility what the product is being used for in medicine, you have to have a clinical trial to use it, because if it's a black box, not a human observer can take responsibility for it. So at least in medicine, I don't think you get around it.
Yeah, I just make a comment on that. I mean, obviously, I alluded to a tool that has been given FDA approval with relatively small retrospective data set testing. And I think one quote, I think from Keith Dreyer, was that we won't know how good all the tools are until they're clinically deployed. And I think it's incumbent on us as a community to understand when something is deployed into clinical practice and is given approval, that we understand at what level it's been tested, because we don't want to stifle innovation and we don't want to stifle important startup companies that are really essential to this field. But at the same time, we can play our part by auditing the outcomes of those tools if they do go into clinical practice. And as I say, I think it's incumbent on us as a community to really understand what testing has been done on that tool, and therefore how can we benefit patient care by properly auditing in clinical practice and actually publishing that information, being in interaction with the company, so that all of these tools can still be developed by innovative startup companies that can get them into the market, but that we're aware at what safety level we're working at, and therefore how much supervision we need to provide.
Thank you. Any other? I've got another question, which is really interesting. I know where it's coming from. What role do you see, and if you see, for radiomics phantom in terms of repeatability and reproducibility and feature selection?
Well, for us, phantoms are a must, no? I mean, we need to use phantoms. Some of them can be digital phantoms or synthetic phantoms, I mean, not only real ones, no? But I really do think we have to check for so many aspects on radiomics and biomarkers with phantoms. But that's not enough. I mean, just with phantoms, we cannot say this is reproducible and this is repeatable because we need patients.
Sure.
And you have a huge amount of variability within patients that have to be taken into consideration. So I do think that's the first step for validation, a must, but not the only one.
So I think also depends how complicated you want to make those phantoms in terms of representing the as closest to reality rather than just a very simple phantom. So actually, that sort of phantom work is something to collaborate with engineers, because the engineering and material sciences have spent their life into looking at different materials, in general. So they will probably have quite a lot of experience on phantoms. Yes, of course.
Can I ask a question to the audience? How many people in the audience would be prepared to take part in a clinical trial evaluating an AI tool? Are people prepared to put the work behind that? Yeah, so we should take a picture of that, Evis, on my phone, and we'll put it on Twitter. Keep your hands up, and we'll put that on Twitter. Who in the room is prepared to help validate tools clinically?
So
have you got a
none of
picture?
you actually know what you're getting inside.
Take hold your hands up. We're going to take a picture, and we're going to put it on Twitter. Smile, yeah.
Excellent.
I just regretted not taking a picture when everybody had their hands up who were collecting data sets. So
She will
my
come
moment.
after you. So it's a very good tweet here, Anwar. Why are we working in image space rather than the raw data space? Do you want to answer that? I also have.
Good. So from our perspective, at least, we are working on roughly 80 different projects around medical data in general. So imaging, and the example that I've given in my talk is just one example of the work that we are doing. And of course, it was mentioned already a few times, you should not see these projects as independent of each other. There are hopefully more and more relationships that we'll find between these projects.
So I think what the tweet was about raw data rather than the image presets. How do you go to the... No, I mean, I think, yeah.
It's a question of availability, because very few centers will keep the raw data, so that's the main issue.
Yeah. So this is...
It's not available.
It stays in the scanner for about 48 hours, having sort of inquired about that. But it's huge data storage, more than, I mean, you can arrange it that it's saved. It's a matter of how do you store that amount of data. But if you do that, that's actually its solution.
Yeah. Well, also you can do that maybe sometimes in some places for prospective studies,
Correct.
but never for retrospective data.
So there is some mathematical work going on actually how do you sort of go backwards and use your deep learning to actually go retrospectively and sort of reconstruct, go backwards. What can I say? Cambridge is a math sort of hub.
Can I ask a question?
Of course. Can you use the microphone?
Okay, in terms of reproducibility, Professor Bonti was talking about. I mean, even the same hospital, same department, if doing a pancreatic CT, everyday protocols changes. How on earth? What are you going to do about standardizing the protocols in the future? I mean, as ASIA has got any plan for this?
Well, I mean, I don't know, I mean, Andrew probably know more, but in our hospitals, our protocols are actually standardized?
But I think it's an excellent
good
question,
yeah.
Because I think if we want to harness AI, we need to come together as a community and have relatively harmonized protocols. Like I said, you want protocols that are harmonized enough that we can harness AI, but that we know that there's going to be variability that we need to be able to work with. So I totally agree with what you're saying. And one thing that I've been very interested with the myeloma study, when I started working on the myeloma study with Christina Messiou, is that the myeloma community have really come together and said, these are the sequences that we need, this is what we need to diagnose the disease. And so now going forward, already relatively early on in the field, most centers will be using a relatively standardized data set. They've published that in MyRads, in radiology, and I believe in prostate MRI. There's been various publications where the minimal data set, if you like, how we should be imaging some of these are published. And I agree that we need to try and come together and actually it's the coding, it's the naming of all these in the RIS systems as well that can allow the identification of the cases, and I think that will help us.
And it actually works backwards too. If you have a application with a clinical proven benefit which works on a specific set of data, the clinicians will actually produce that set of.
Yeah, I think it's one more quite interesting, and then we'll have to break for coffee. So recently an Israeli researcher developed an infected imaging data with a virus to simulate lung cancer. What kind of measures are companies providing to cloud-based models that are taking to mitigate such risks? So how are you protecting us? I'm just looking at poor Stefan. It's the only company. I don't think I'll make it to Cambridge tonight, tomorrow.
Okay, good. That is actually a good question. I don't know this particular case, so I will not go into the details of what happened in Israel. Having said that, we are taking the necessary security measurements, so we are sure that we take things like identification of the person and the organization who's sending images to the cloud, the complete encrypted security channel and so on. We take that really, really serious. So we are doing security audits on the software that we are developing. That is for sure. And that is what we can do, I think, and that with proper identification where the source is, where the image coming from, is how it could work.
I mean, I think yes. I mean, I think it's crucial, but you know, that is what the Twitter raise is actually crucial, because what happens if you do all that protection as a company or as a hospital, but then actually your algorithm is messed up rather than actually the quality or the anonymization of the data, so you're not detecting the right abnormality, or, I mean, it's something, it's almost, yeah, it's just difficult. Anyway, on that note, unless it's a burning question, because we're actually, I think it's almost, we're over the time. I know, but we're over time. I think probably during the coffee break. Yeah. Thank you. Sorry. One has to make decisions.